coronavirus pandemic led to a huge shortage of face coverings in the market. This left a lot of people, especially frontline workers, in a vulnerable position without the most basic line of defense. N95 masks are one of the most effective masks available in the market, but are designed for a single use only. The purpose of our project is to develop a system that creates the optimum conditions for disinfection of N95 masks, which will alleviate some of the issues of shortages in the market until more masks are available.
To achieve disinfection, a project team developed a system with the help of Dr. Bilal Mansoor of Texas A&M University at Qatar to disinfect an N95 mask. To disinfect this mask, it is placed inside the sealed container at a temperature range of 70 to 80 degrees and relative humidity of 60 to 85%. The temperature was set by using a commercial oven in the experiment, and the main measurements to be taken was of relative humidity. Humidity was varied by placing a tissue soaked in water inside the container. As such, our primary objective was to measure the amount of water to be used to achieve the required conditions.
The sensor we are using for this experiment is an SHT30 sensor that measures temperatures between minus 40 degrees Celsius and 125 degrees Celsius. The same sensor can also measure humidity between 0 and 100% relative humidity. The SHT30 sensor has a small size of 17 by 12 millimeters. This makes the sensor very convenient to use in our experiment, as it is small, so it can be placed easily inside the container without having to drill holes into it.
First, I will place a paper towel inside the box. Now I'll add some water. SHT sensor is already in the box. I'll close the box and immediately run the program, which will record the data and export it to Excel sheet. Now I'll place the box inside the oven.
The oven is preheated and we will let the experiment run for 30 minutes.
In analyzing the data, we opted to choose the point where the inside of the container reaches 70 degrees Celsius as the starting point of the analysis. This is because 70 degrees is the beginning of the specified temperature range, and that way we can make sure that the initial conditions with regards to temperature are the same for all volumes of water added. For 3 by 3 centimeters, you can see that for the added water volumes, the graphs align beautifully as they follow the same shape for a temperature of 70 degrees Celsius plus. We can also appreciate the effect of adding any amount of water to the container by looking at the empty box curve. The positive takeaway from the 5 by 5 centimeter plot is that for 1 milliliter, the relative humidity is within the range from start to finish. However, for 1.5 milliliters, RH exceeds the range as it reaches 90%. From these figures, we may observe that, as you would expect, there is a positive correlation between volume of water added and maximum percentage RH reached. The average temperatures with their standard deviations are also plotted to confirm that the temperature ranges for each of the runs were similar.
To conclude our experiment, we set out to find the right amount of water to be used to achieve the set conditions of relative humidity at a constant temperature. For our conditions, we found using 0.5 ml to 1 ml of water heated at 70 degrees Celsius would successfully maintain the RH between 60 to 85% for approximately 30 minutes. While we were at it, we also found an inverse relationship between the relative humidity and temperature when there is no water source in the container, with the relationship changing when water is added to the container. Comparing the 3 by 3 centimeter tissue with a 5 by 5 centimeter tissue, we also found that the 5 by 5 centimeter tissue reached the humidity range earlier and maintained it for a longer time, meaning the surface area of the water medium used also had an impact on the experiment, with a larger surface area leading to an increase in water evaporation and finally increased relative humidity.